Welcome to this presentation for EMS627U, Modeling and Control of Robotic Systems. This is the video presentation for Part B of the coursework, Control of Wheeled Mobile Robots. It documents how we built, tested, and controlled the Turtlebot 3 Burger model using ROS. It includes robot assembly and standalone mode tests, simulation in gazebo environment, implementation of SLAM algorithm, teleop control using the keyboard, real deployment, and obstacle detection examples. We began by assembling the Turtlebot 3 Burger's hardware. Before configuring the network, we validated our build using the standalone mode. By triggering the OpenCR board's built-in test sequence, we confirmed that the motors and sensors were fully operational independent of the remote computer. We pressed a button that made the robot do a 180 degrees turn and another that made it move 30 centimeters in a straight line.
Before launching any ROS nodes, we verify the wireless link between our remote PC and the robot's Raspberry Pi. We use the ping command to target the robot's IP address. As you can see on the terminal, the consistent packet returns and low latency values confirm that both devices are successfully networked. This step is critical to ensure there is no lag when sending velocity commands later.
With hardware and connection verified, we transitioned to the gazebo simulator. We launched the virtual Turtlebot 3 model to test our control logic in a safe environment. Using keyboard teleoperation, we drove the robot within the simulation, validating the kinematics and ensuring the software environment was correctly configured for further tasks.
Next, we established manual control of the robot using the keyboard teleoperation node. With this tool, we can directly command the robot's movement through simple key presses. By using WASD and X keys, we send linear and angular velocity commands to differential drive controller, allowing us to steer the robot forward, backward, and rotate it on the spot.
Next, we moved to implement simultaneous localization and mapping algorithm called SLAM. We launched the mapping node along with the Arvis visualization tool you see here. As we teleport the robot through the environment, pay attention to the laser scan data, visible as the colored points hitting the boundaries. The algorithm uses these recordings to construct a 2D occupancy grid map in real time. You can see the map updating as the robot moves around the box.
Finally, we deployed the obstacle detection node to demonstrate autonomous control. Watch how it reacts to the object ahead. The LiDAR sensor detects the obstacle within the program safety threshold. This triggers the avoidance logic you see in action, halting the robot immediately to avoid collision.
In conclusion, we successfully transitioned from simulation to real-world deployment. Validating Gazebo first allowed us to safely execute SLAM and obstacle detection on the physical Turtlebot 3. This completes our presentation for EMS627 Part B. References and acknowledgements are currently displayed on the screen. Thank you for watching, and I hope you enjoyed.